Today, we're doing our quiz. We're going to review Chapter 10, and then we're going to learn 11.1 today. Sunday, you have your next homework due on Connect Math 10.1, and then Tuesday, a week from today, you'll have Connect Math 10.2 due. Don't wait till the last minute. Start on those now. No reason not to start on them now. Next Thursday, a week from Thursday, you'll have 11.1 due, so nothing for a little while. Don't forget, exam 4 is rolled into your final. So that means that your final is going to be weighted very heavily on chapters 10 and 11, since exam 4 is a chunk of that. So 35% of the final is going to be the stuff we're covering yesterday, today, and Thursday. And we'll kind of finish up with it on Monday. The rest of it will be about 20% from exam 1, 20% from exam 2, and 25% from exam 3. Their final is December 16th, so 2 weeks from Thursday. Yours is at 5:30, so yours starts a little bit later. If folks want to come in and start at 5, who would prefer to start at 5 o'clock? Who would prefer to start at 5:30?
The final.
Would anybody prefer to start at 5:30? I think you're kind of outvoted.
Maybe
Okay.
it's 5.
At 5.
Okay.
5 is good.
All right. So if one, you can come at 5:30. Okay, but then you'll miss my final talk to everybody. So I don't know. All right. So we'll discuss that more, I guess, as we go along. So whoops, that's too far. We're not there yet. My bad. So let's review chapter 10 first. How about Nathan, go read for me?
Correlation determines if a linear relationship between variables exists. Regression describes the relationship between variables that is positive or negative, linear or non-linear.
Right, so we're doing this chapter. And we're answering these 4 questions. 1, are 2 variables related? If they are, how strongly are they related? What type of relationship exists? And most importantly, what kind of predictions can we make based upon this relationship? That's kind of where, that's the important part of statistics, one of the important parts of statistics. Scatter plots, right? That's a graph of the order pairs x comma y. X is an independent variable, the one you have control over typically, and y is the dependent variable. All right, I need a good reader.
The population correlation coefficient, denoted by
Rho.
Is computed by using all possible pairs of data values x, y taken from a population. The linear correlation coefficient, denoted by R, is computed from the sample data and measures the strength and direction of a linear relationship between 2 quantitative variables. The one explained in this section is called the Pearson product moment correlation coefficient, Ppmc.
Right, so we're using our Ppmc table. Again, remember this is rho. It's not P, so don't use P. It's this kind of long bar that kind of curls around on itself, kind of slanted. Or just write rho, R-H-O. Right, so it's totally fine to just use the phrase rho instead of this, or this long sort of curly thing. Okay. The range of correlation coefficients is from -1 to +1. Strong positive correlation has like if it's a perfect line, it would have a correlation coefficient of 1. If it was a perfect line with a negative slope, it would have a correlation of -1. If it has no correlation whatsoever, it's smack dab in the middle, that's 0. And remember, I like them because they sort of match up with kind of how you expect to picture them. Right, here's a line with a positive slope that looks like a 1. There's a line with a negative slope also looks like a 1. And then just a whole bunch of dots randomly looks like a ball. That's how like 0. Right, so it matches pictorially with what you'd expect. So everybody, this is not on your quiz. It's not on your paper. This will be similar to a question you might get on the exam. So on your quiz, pick from those numbers, fill in what correlation coefficients can match up with each one of these pictures. So write 4 numbers across the top, 3 numbers along the bottom, And you do not consult your neighbors because this is one where just think of it, treat it as a practice final question. Number 100. None of them. What's the largest correlation coefficient can be? 1. What's the smallest it can be?
-1.
So these all do not exist. 100%. Okay, so which one's the easiest one? Which one's 1?
3.
Yeah, so which one is, what's this one below it?
-1.
What's this one with no random anything? 0. Great. So then these two are the positives. This one's 0.8 since it's closer to a line is closer to 1. This is closer to -1, so this is -0.8. This is -0.5. The sample correlation coefficient R. We are not going to use this big, long, complicated formula. Instead, we're just going to use, we're going to put the x's in the list 1, the y's in the list 2, and we're going to use stat test linear t-test to find our R. Round R to 3 decimal places because that matches up with the Ppmc table. So here's our hypothesis test. Step 1, probably the most important one. Lauren.
In hypothesis testing, one of the following is true. H naught equals rho equals 0. This null hypothesis means that there's no correlation between the x and y variables in the population. Rho equals 0, no line. H1 is rho does not equal 0. Sorry?
H1 is, yeah.
Oh, H1 is, sorry. Rho is not equal to 0. Rho.
Don't worry about this.
Okay.
This is just the last semester when people had to type it in on the
Okay.
computer. Yeah, no worries.
This alternative hypothesis means that there is a significant correlation between variables in the population. Is a line.
All right, so again, remember H has all the no's. No correlation, no difference, no line. Right? So then H1 is that there is a correlation, there is a line, there is a difference. Second step is you're going to use the Ppmc table. Based upon your alpha, your level of significance is your alpha. That'll tell you which column to use. And then degrees of freedom is n minus 2. I know we used to have it being n minus 1, but that's because we usually have one variable. Now we have an x and a y. We have 2 variables. So degrees of freedom minus the number of variables we have. Since we have an x and a y, it'll be degrees of freedom is n minus 2 now. And you'll see it at the top anyways. So that tells you which row to use. And then you slide along that row to the correct column to find your critical value. Remember, what you want to do is, once you find your critical value, remember this is -1, that's 0, this is +1. You're going to figure out where your critical value is, shade, and it's always two-tailed. So that's your negative critical value. Kind of a poor negative side. Made it worse. Okay. Because I don't care whether I am negatively correlated or positively correlated. I just care that I'm correlated. So it's always going to be two-tailed. And it can be negative correlated or positively. I just want to know if it's a line or not a line. All right, so here's the first problem. Destiny, go ahead and explain what you did.
Okay, so H naught is always rho equals 0. H1 is rho is not equal to 0. You find your CV by there's 12 total, so you subtract by 2 to get 10. Look at the chart, it's plus or minus 0.576. You create your little graph. Once you put in the data, you'll get that R equals 0.9409. Since it's in the shaded region, you're going to reject H naught, and in addition, it's also going to be positive correlation between the two. So there is enough evidence to fourth plane with positive correlation between the amount of drugs and reaction time,
How'd you know it's positive?
because it's on the right side.
Yep, this is close to positive correlation 1. You don't need to do that, but that's kind of a nice extra step.
Okay, and then once you try to find the reaction time would be given with x, which is 5.2. You just plug in the numbers. You find a and b on the actual calculations that you did. And with that, you get 3.33. So the reaction time is going to be 3.33 seconds.
Right, so she put in 5.2. Why did you put in 5.2 for x? Why did you put it in for y? So 5.2, how'd you know that was your x and not your y?
Because they're percent.
Because it's a percent. So you look here and say, oh, the percent is my x. So you know that that's your x. The other thing I wanted to point out is this part right here, where it says reject H naught. So whenever we reject H naught, then there is enough evidence, right? And it is aligned. If we do not reject H naught, then it's not enough evidence and it's not aligned. So the knots all go together. So and catch that. So if there's not enough, if we do not reject H naught, there's not enough evidence, it's not aligned. Not. Here in this case, we do reject H naught, so there we do have enough evidence and it is aligned. Okay. Good. All right, so then regression, that's that line of best fit, or least squares line. It's that straight line that best fits our data, the scatter plot. So how do you find it, or how do you find it in the old days, or how does the calculator find it? It takes every single point, and it finds the distance straight up or down to the line. It squares that distance, and it adds them all up. And the line that has the least sum of the squares, that's your regression line. That's what I call the least squares regression line. Please note, this line is used to predict the values of y for a given x only when you have a correlation. Only when your data is aligned. If your data is all over the place and is not aligned, then you can't use a line to predict it. Right? If your data is not significant from 0, in other words, it's kind of scattered around, then sure, it'll give you a line, but using the line is ridiculous because your data isn't aligned. So, as I mentioned earlier, if you do not reject H naught, then it's not aligned. Those knots go together. Which means you would not use the line y equals a plus bx. I showed you this last class, but I thought I'd show you folks again. Right, remember this is those two, you can both agree that both of these do not have any sort of order to them. And this one has a regression line that slopes up slightly. But if I just remove these two spots here, then all of a sudden, this same graph slopes downward slightly. Right? And so you can really see how silly it is to pay attention to that line at all. Instead, you should use this red line, the average, instead. That's your best predictor. In other words, we all know that shoe size is not correlated to exam scores. So if our class had an average score of 90 on the last exam, what's my best guess that if someone has a size 14 shoe, what's my best guess at their exam score?
90.
90, the average, the sample mean. If they have a size 4, what's my best guess at their exam score?
90.
90, the average. Right, so no matter what the x is, my best guess is the average. There's a regression line. Again, y equals a plus bx, and you're given this in your calculator when you do stat test, linear t-test. I also want to point out one other thing which is really interesting. This is called Anscombe's Quartet. It's pointing out the fact that you can take these are 4 different graphs, and it points out the importance of actually seeing the graph to recognize, not just going off the numbers. So these all have the exact same R, the exact same correlation coefficient, and the exact same linear regression line. But you can see they're totally different, and really only one of them should follow that linear regression line. So that's the way that data can be manipulated in strange ways. Now I'm not going to cover that because it just takes too long to graph it. But you should just be aware that you can have some oddball cases out there where the numbers are not the whole story. So let's take a look at the second problem. Isla, go ahead and explain what you did.
Well, I started by doing the hypothesis test to see if they're even linearly correlated. So you start first step where H naught is rho is 0, H1 is rho is not 0. And the second part, alpha is 0.05, and the degrees of freedom is the number of values 7 minus 2, which is 5. And then using the chart, you can find that the critical value is plus or minus 0.754. And then I drew it on the little number line. For the third step, I found R by doing the linear regression t-test on the calculator. I plugged in the L1 and L2, which I copied from the charts. Found that R equals 0.4446. And then I drew that on the line. And then that is not within the rejection region, and so you don't reject H naught. And because you don't reject H naught, there is not sufficient evidence to support the claim of a linear correlation between casino size and revenue, which means that when you're making your predictions, since there's no linear correlation, the best estimate is your sample mean, which is the mean of Y values or L2. And so then I plugged that into the calculator and got $134.714 million.
Good. Perfect. Right, so when your data is not aligned, when you do not reject H naught, it's not aligned, you can't use a line. Instead, you use the average Y. How do you find the average Y? You already have it in your list anyways. You have it in list 2 typically. So just do stat calc 1 bar stats of L2. Or you could do stat calc 2 bar stats of L1 comma L2, and then it'll show you the Y bar. Yeah?
It's a different answer if you do 2 bar stats.
If you do 2 bar stats, you should get Y bar.
There's Y bar in there.
Or you could do stat calc 1 bar stats of L2, not of L1.
That's right. Yeah,
So-
we got it now.
Okay. Yeah.
Yeah, we did extra.
Right, so don't do stat calc 1 bar stats of L1, because that'll get your average X's. So just, yeah, be aware of that. That's great. Thanks for pointing that out. Nice. All right. So our learning objectives for chapter 11. Here's that. Oh, yes. So your handouts that I gave you have for today, the first 3 pieces of paper are chapter 10, which you already have. Just tear those off carefully so you don't mess up your staple for the rest of it, and throw them in the garbage can later on. Okay, everybody good? So the first, somebody give me yours. Okay, so these first 3 pages are chapter 10 notes, which you already have. So just take those 3 pages and get down to the chapter 11 notes. Rip them off carefully and toss them later on. Okay, good. So now we're going to get into 11.1. So what we're going to do in 11.1 is we're going to test for goodness of fit using the chi-squared. Everyone, it's chi like kite, like the first part of kite, like ky kind of, or ki. Someone say chi. Chi, great. It's chi-squared. Does not mean you take a chi and you square it, or take an x and you square it. It's its name. Its name is chi-squared. Good? Okay. So let's get a reader. Lindsay, go ahead.
The chi-squared statistic can be used to see whether a frequency distribution fits a specific pattern. This is referred to as the chi-squared goodness of fit test, which tests the claim that an observed frequency distribution fits some expected frequency.
Perfect, thank you. So, exactly, we're testing that what you observe matches what you expect to get. So, your book will call it many other things using words and stuff like that. I've just simplified it to make it a little bit cleaner for everybody. We're saying that the observed values equal the expected values. So it's O sub I equals E sub I. Why is it sub I? Because there's several observers you're going to have, one for each category. So in chapter 10, we talked about means, about numbers. You had Y bars and X bars and things like that, right? Now we're talking about we're talking about proportions. So it's kind of like binomials, only instead of having only two options, yes and no, now we have multiple options, multiple categories. So like, eye color could be brown, blue, green, hazel, bloodshot, I don't know, whatever. But, all right, so there's multiple options, not just two. Right, so these are going to be proportions. These are going to be frequencies. And our data is going to be categories. Does that make sense? So our data is going to be, what's your eye color? Blue, green, brown, stuff like that. It's going to be, your data is going to be, is going to be categories. Does that make sense? So that's what we're looking at here. So we're saying for each category is the number of brown eyes matching the number of expected brown eyes. Is the number of blue eyes expecting the number of blue eyes I get match what I expect to get. Is the number of green eyes matching the number of green eyes I expect to get. So that's what that's what we call it sub I, because it's for each category. H1 is that what we observe does not match what we expect. So again, not equal to. So you might think it's two-tailed, but here's the deal. Everyone grab out your chi-squared, or grab out your Ppmc table that you've just been using. The back of it is your chi-squared table. If you look at the picture on the chi-squared table, I'm going to take a gander at that. See how it starts off at 0 on the left? And it goes off to the right? So it starts at 0 and only goes in one direction. It only goes to the right. So it's automatically only one-tailed because it always starts at 0 and it can only go one direction. So that means that if you're near 0, then you're fine. If you get too far out, then you're unusual. If you're too far to the right. Okay. Good deal. Here are some assumptions. One is your data has to be from random samples, and the expected frequency for each category has to be 5 or more. Oh, that's a good reason. That's another good reason why you can't have decimals. We'll talk about that later. You can't have percentages. All right. Here are some comments about it, which are in your notes. We'll have Nicole go ahead and read for us.
Observed and expected frequency. O represents the observed frequency of an outcome found by tabulating the sample data. E represents the expected frequency of an outcome found by assuming that the distribution is as claimed. K represents the number of different categories or outcomes, and N represents the total number of trials or observed sample values.
Perfect. So here's our test, chi-squared. It's also the same thing as our test stat, so you can just call it your test stat if you prefer instead. Just keep things simple and easy. So how do you compute it? Remember, does not mean take x and squared or take chi squared. That's just its name. That's its symbol. Good. So again, like I said, you can just call it test stat if you prefer. What you do is you take every observed value, subtract its expected value, square that amount, and divide by what you expected to get for each category. And then you sum them, you add them up. One thing I might comment on is the degrees of freedom is the number of categories minus 1. Why is that? Because how many things am I adding? Well, O minus E squared divided by E. I'm going to do that once for every category. So the more categories, the more things I'm adding up. So you follow? So I'm doing this O minus E squared divided by E once for the blue eyes, for the green eyes, for the hazel eyes, for the brown eyes. So the more categories I have, the more things I'm adding. That's why the degrees of freedom depends upon how many things I'm adding by categories. So it's the number of categories minus 1 is my degrees of freedom. Because it has to become larger the more things you're adding. All right, so let's get into an actual example because that'll make more sense. So here we have flavors of soda. Cherry, strawberry, orange, lime, grape. I don't know, it bothers me that there's only 10 people who like grape because I think grape is the best, but hey, it's all right, no worries. What they're claiming is that there's no preference in the flavors of fruit soda. So no preference. If there really is no preference, then to yourselves think about this. How many would I expect to be in each of the categories? They surveyed 100 people. How many do we expect to get in each category? Think about yourselves for 15 seconds.